Hello, Sancho Nerds. Before we begin, I just want to say that I'm currently writing a draft for my guide, which you can download on my website on Sanchoneering. It has equations, descriptions. I'm also in the process of writing some other ones, like fluids. As of January 2019, it's currently free, but that's subject to change, so I'd grab it if I were you before that changes.
Good morning, you Sanction nerds. Welcome back to Sanctioneering.
Sanctioneering.
Last time we talked about some linear interpolation, but I think we're going to move on to some fluid physics. All right, so this is going to be straight from my Sanctioneering guide that I'm writing, so you can feel free to download it on my website,
Sanctioneering.
And so today, if all you care about the equations, we're just going to talk about some fluid physics, including flow rate, and a bit of review of density, as well as some hydrostatic pressure equations. All right, so today is all about fluid physics. And I really want to get into fluid mechanics, but we're not quite there yet because we're going to be dealing with steady state, which I'll talk about later. And fluid mechanics deals with non-steady state, as we'll see in the future. Okay, so first, what is density? Density. So you may recall that density is defined to be the ratio of mass to volume, right? You may know that if you have a block, little block right here, and let's say this is a 1 by 1 by 1, a 1 cubed centimeter cubed block, and let's say it weighs 1 gram, then you would say the density is 1 gram per centimeter cubed. Okay? And we've done some equations and some conversions using density. So if you haven't checked those videos out, go ahead and check those out. They're on the playlist. And what else can we talk about? We can talk about flow rate. And with flow rate, there's two types. There's mass flow rate and volumetric. Okay? So what do I mean by that? So let's say we have a fluid flowing through a pipe. So I'm going to draw a horizontal cylinder. Oh, Lord. So this is my pipe. And some fluid is going in and out of the pipe. Okay, so this has some flow rate. So the mass flow rate is denoted by an m with a dot on top, and the dot means that you're going to take the mass going through the pipe and divide it by the time. Okay, and similarly, volumetric flow rate is defined as a v with a dot on top, and that's the volume going through divided by time. Okay, so the dot on top means you're just dividing time. So if this is water flowing through, this is going to be m dot and v dot. Okay, so flow rate is just simply however much of something is going through something else. Okay, so in this case we have water going through a pipe. Okay, and so in combination with density and flow rate, we can write a couple other relationships. You may notice that I spelled physics incorrectly. My bad. Okay, remember that in this case, since this is a pipe, this is going to have a cross-sectional area. So the cross-sectional area is this area that it's crossing through. So let's kind of shift our minds and see if we can visualize that. So we're going to have this circle. So this is going to be the cross-sectional area, and you'll know that it has some radius. So the cross-sectional area is going to be pi r squared. Cross-sectional area is nothing other than just you're taking an object, you're slicing right through that middle, and the area that that slice goes through, that's your cross-sectional area, as opposed to surface area, which is the area that covers the surface. Go figure. So let's play around with density a little bit more. If we say that density is mass over volume, well, I'm going to multiply by 1. If I multiply by t over t, that's just 1, which is something that I can do. And I'm going to divide this mass by this time and this volume by this time, which means I'm going to have m over t over v over t, which I just defined m over t as m dot and v over t as v dot. So we have a nice little relation that can be useful later, saying that rho not only is mass over volume, but it's actually m dot over v dot. Okay, so it's not only the ratio of mass to volume, it's the ratio of mass flow rate to volumetric flow rate. Okay, let's continue a little bit more. If I say that density is mass over volume, I hope you can see that mass is density times volume. I'm just multiplying both sides by volume. And let's see what we have here, density times volume. So if we have this as the cross-sectional area, then volume should be, first we got to define the length, in this case of a cylinder, let's just call it L. Then the volume should be the cross-sectional area times the distance, right? That's the volume of a cylinder. This can be applied to the volume of a cube or any other simple geometric shape. So if mass is density times volume, then that is going to actually be density times volume, which is the cross-sectional area times length. Rho A times L. Okay, cool. Now what happens if I divide both sides by t? So let's rewrite that here. If I have m over t right over here, I'm going to skip this part and I'm going to divide this entire thing, rho A L divided by t. Well, we know that m over t is m dot, and we know rho A L over t. Does that sound familiar? Well, L is the length or the distance divided by time gives you velocity. That's right, from physics. Rho A times v. That's the vector notation. Cool. So we just kind of got the intuition for a nice little relationship that might be useful. A little bonus, let's do a little bit of dimensional analysis on this guy, shall we? So, check out my dimensional analysis videos if you haven't seen those already. So m dot is going to be in the dimensions of, right over here, m over time. And rho is going to be mass over length cubed, because it's volume. Area is going to be length squared, and velocity is going to be length per time. So I hope you can see that if I cancel out this L squared and this L with L cubed, we're going to be indeed left with mass per time. So the dimensions do check out. Okay, so that's it for this little introduction to some fluid physics. Oh, I guess I didn't do hydrostatic pressure. Let's leave that to the next video, shall we? Click the link in the description to go to my website. You can download the PDF, or you can click the other link in the description to get to the playlist for chemical process analysis. In the next video, we're going to do some hydrostatic pressure. Maybe we'll do some problems. If not, we're going to go to mass balance. If you enjoyed this, don't forget to share this with your friends, family, and your dog.